Hello, I want to introduce the concept of complex impedance, or how we can simply apply an equivalent to Ohm's law to capacitors and inductors. As we've seen, for nodal analysis, you need to apply Kirchhoff's current law to any nodes not at ground or a known voltage, and then you need to apply an equation relating the current through a component to the voltage across that component. Now, what we've done before for capacitors and inductors is apply the differential equations. Current equals C dV dt for a capacitor, and voltage equals L di dt for an inductor. That results in a set of simultaneous differential equations that we have to solve. This can get tricky, but there is an easier way. Life would be very easy if all of the components in our circuit were resistors. For resistors, the voltage across the resistor is proportional to the current flowing through it. So we don't get any differential terms in our simultaneous equations. If we used phasors to represent our current sources and our voltage sources, we would just end up with a set of linear simultaneous equations. The only slight difficulty is that the voltages and currents in those simultaneous equations would be phasor representations of the oscillations, so they would be complex numbers. But apart from that, solving the resultant set of linear simultaneous equations doesn't prevent any particular difficulties. The problem, of course, is if we don't just have resistors in our circuit, we have capacitors and inductors. Then the equations that a nodal analysis would result in contain these differential terms, or if we wanted to write them in the integral form, an integral term. And now solving them is considerably more difficult. But I did promise that there was an easier way. What if all of the voltage and current sources in the circuit were sinusoids rather than cosine waves? I should first define what a sinusoid is. A sinusoid is a complex oscillation. It obeys this formula here. Zt is A times e to the power of j omega t. Now, a complex number can be written in polar form as a e to the j theta, where theta is the phase of the complex number. So that would be, for example, this complex number here, where its distance from the origin is a, and the angle to the real axis is theta. Replacing theta with omega t results in a complex number whose angle is a function of time and is increasing linearly with time. If this angle is increasing linearly with time, then the complex number here ends up going round a circle. It's always a distance a from the origin, because the a is constant, but the theta, the phase term, is just equal to omega t. It is increasing at the rate of omega radians every second. You can also write them like this. A e to the j omega t, a cosine omega t, plus j a sine omega t. The sum of a cosine wave, a real cosine wave, oscillating like this, and an imaginary sine wave oscillating like this. Add those two components up together and you end up with a complex oscillation which rotates around the origin, always maintaining the same distance from the origin. Right. A couple of very interesting properties of a sinusoid like this. The first is that if you differentiate it, you end up with the sinusoid times j omega. So dzt dt is just j omega times A E j omega t, which is just j omega times the sinusoid that you started with. And if you integrate it, you get a similar result. The integral of zt with respect to t ends up being 1 over j omega times z of t. The other nice thing about sinusoids is that they share the property with sinusoidal oscillations that two sinusoids at the same frequency, if you add them up, you get a third sinusoid. So, if all the voltages and currents in my circuit are sinusoids, then a capacitor would behave just as if it was a resistor with a resistance value of 1 over j omega c, because the ratio of the voltage to the current for a capacitor, Vt over It for a capacitor, ends up being 1 over j omega c. And the ratio of the voltage across a inductor to the current through an inductor ends up being j omega L. And for a resistor, V of t over I of t, that ends up just being R, the value of the resistance. That is just Ohm's law. These behave like Ohm's law because as long as the frequency is a constant, then this is a constant for your circuit. And so is this. The ratio of the voltage across the capacitor to the current through the capacitor is a constant and just equal to 1 over j omega c. This idea is so important that I'll summarize it on this slide. Resistors have a current equal to the voltage across them divided by their resistance, so they behave as if they have an impedance of R. Now, I'm used the word impedance here rather than resistance. Impedance is a generalized form of resistance. Resistance is usually used specifically for real voltages, real currents, whereas an impedance can be imaginary or complex. For a capacitor, if I've got a sinusoidal current and a sinusoidal voltage, then the ratio of the current to the voltage is j omega c, which means they're behaving just like a resistor with an impedance of 1 over j omega c. And for an inductor, the ratio of the current to the voltage is 1 over j omega L, which means they're behaving just like they have an impedance of j omega L. So now, for all of these types of component, we have a current through the component proportional to the voltage across the component, which means all of the results that we've previously derived for resistors using Ohm's law can be applied to capacitors and inductors as well. You just have to consider that the impedances of these capacitors and inductors is imaginary. At this point, I'd like to introduce you to a useful mnemonic, the acronym CIVIL. It stands for capacitors. The I stands for current, because we usually use I as a symbol for current. We can't use C because that would be confusing with capacitors. The V does stand for voltage. The second I also stands for current. And the final L stands for inductors. We can't use I because we're using I for current, so we use L for inductors. The mnemonic works by listing the current and the voltage in the phase order which they appear. The idea is that it helps you to remember that for a capacitor, the current is 90 degrees ahead of the voltage. It happens first. If we were to plot the current and the voltage across a capacitor against time, then if the current was doing this, maybe the current was a cosine wave, then the voltage would be doing this. not terribly good drawing. Sorry, it's better down here. This is the voltage. This is the current. The current goes through its maximum first. It comes up through 0 before the voltage. So the current oscillation is ahead in phase of the voltage oscillation. For an inductor, the reverse is true. The voltage would be ahead of the current for an inductor. So if I drew the corresponding graph for an inductor, I would end up with something like this. This now might be the voltage, and I'll see if I can draw it better this time. Something which is behind the voltage would look like this. Goes down, negative, up there, down here, down. That's a bit better. For an inductor, this is the current. This is the voltage. And you can derive that this must be true from the impedances of these two components, sometimes called the complex impedance because in general they're complex. For a capacitor, the current is j omega times CV of t. Well, j is e to the power of j times pi over 2, or 90 degrees. Times omega c and v, and omega c is real. And multiplying something by e to the j pi over 2, or just j, effectively rotates it through 90 degrees on the Argand diagram. So, if my voltage was, for example, has to be a sinusoid, so A times e to the j omega t, then the current would end up being omega c times A e to the j omega t plus pi over 2. So at time t equals 0, if the voltage was here, the current would be here. And as the voltage moves round, the current would move round and always remain pi over 2 radians, 90 degrees ahead of the voltage. For an inductor, it's the other way around. Civil is just a convenient mnemonic to quickly remember whether the current is going to be leading the voltage or the voltage leading the current. Yes, as some of you will no doubt have noticed, there is a fundamental problem with all of this. In the real world, there is no such thing as a sinusoidal oscillation because all voltages and all currents that happen in real circuits in the lab are real. So does that mean that all of this nice theory is useless? Well, no. Thanks to the work of a guy called Joseph Fourier. You'll be learning a lot more about Fourier's theories later. For now, we just need this key result. Any real signal can be expressed in terms of a weighted sum of sinusoids. So as long as we have a linear circuit with just capacitors, inductors and resistors in it, no diodes or any nonlinear component like that, then we can just express our real voltage and current sources in terms of a sum of sinusoids, solve our circuit for each of these sinusoidal sources, and then use superposition to combine all those results. That may sound like a long process, but there are a couple of shortcuts that we can use to make things even easier than that. Okay, next time we'll have a look at a few examples of complex impedance.